In this graphic, I think it's really cool. As you can see, it's the top of many batteries. So, and again, Electrochem is going to be really cool because you'll actually understand really a lot of ways that you're using chemistry constantly in your daily life. So with Electrochem, we've got the study of the interchange of chemical and electrical energy. The basis of this is going to be a redox reaction. So all batteries, so you can think of, name as many types as you can think of, all batteries are chemical reaction that's producing electricity, which is really this transfer of electrons and doing some very useful work for you. So they are redox reactions at work. There are two processes going on with oxidation and reduction. Oxidation is where electrons are lost by one substance, and reduction is where those electrons that are lost are gained by another substance. So that flow of electrons is what we're going to be using to do some work for us, like power your cell phone or your computer or a flashlight or anything. Oil rig is a great mnemonic device. Oil stands for oxidation involves loss, and rig stands for reduction involves gain. And when we talk about loss and gain, we're talking about of electrons. That's the important key to redox, that flow of electrons. I like to use LEO. The line says GER. Either one, great, helpful instruments. LEO stands for losing electrons is oxidation. GER, gaining electrons is reduction. So just helpful things to remember so you won't get them confused. And again, since one substance is another substance is gaining, we cannot have one without the other. So in a reaction, we can't have two oxidations, we can't have two reductions. We must have something being oxidized and another substance being reduced. So just as let's just kind of look at these. These are called half reactions. Notice they don't look like normal reactions because you see electrons. So looking for reduction, again, we said either with rig, reduction involves gain of electrons, or GER, gaining electrons is reduction. Either way, think about if electrons are being gained, that means they're a reactant. So where in these examples do we see electrons as a reactant? So reduction would be 1, the copper example, and the aluminum ion example. So, and if we see here, we're going to get to where these, how these numbers come into play. But notice copper 2+, that's an ion, so its charge is actually going from 2+. When we have a solid piece of metal, we say it has an oxidation number of 0. It doesn't have an overall charge. You think of it as being neutral. So you can see that 2+ plus 2 electrons is how we got to neutral 0. Same thing with aluminum, 3+, took 3 electrons to get it to 0. And notice the great thing about reduction, the numbers actually do what we're saying. Reduction involves gain of electron, the numbers actually go down. They're actually reduced. So +2 to 0, +3 to 0. That's a helpful thing to note. So if we're looking for oxidation, it would be the opposite. Again, we said oxidation involves loss of electrons, or losing electrons is oxidation. Losing means, think of a product. The electrons for these half reactions are going to be on the product side, and the oxidation numbers, because you're losing negatives, the oxidation numbers actually go up. So if you see from solid iron, which is 0, for it to go to 2+, it had to lose 2 negatives, 2 electrons. And for silver, which is normal ionic charge is +1, silver to +1 would have to lose 1 electron. To really understand some details in more complicated examples, because sometimes we'll have polyatomic ions, as you see at the bottom of the slide, permanganate ion. And you'll need, because you'll actually have to know what is the individual oxidation number of the Mn in the permanganate ion and of oxygen in the permanganate ion. So there's a little bit more details we need to discuss, but as we saw earlier, single atoms that are solids like copper, or we saw aluminum, those are neutral. their oxidation number we say is 0 because they don't have an overall charge. And if we have a single ion, which the technical term is a monatomic ion, like Cu2+, if it's a single ion, whatever its ionic charge is, that is its oxidation number. But let's go over all the rules because you'll need to know some other ones in the future. So number 1, just as a review, elements have an oxidation number of 0. Here are some examples. Some metals, copper, iron, sodium. But then also you think about nonmetals. We have our diatomic molecules, like oxygen exists as oxygen gas, O2. That's its elemental form. O2 has an oxidation number of 0. Same thing with H2. And there's some other elements you might see like P4 or S8. Again, those are elemental forms. We would assign those oxidation numbers of 0. Number 2 of those monatomic ions I mentioned earlier. If it's a single ion, whatever its charge is, that is what we consider its oxidation number. So you see there's copper 2+ again, and then if you look at some negative ions at the end, you've got chloride, which is -1. That would be its oxidation number or oxidation state. Sulfide, it would be 2-. And then we get into a few different just reminders here. Fluoride is the most electronegative element. It will always be -1, period. Okay, we're not going to see cases where it would be anything other than -1. So that's going to be what to remember later. Number 4, hydrogen. If hydrogen is acting as a metal, like it's with a nonmetal, we're going to give hydrogen its +1. So you'll see this in acids in many cases. So +1 if hydrogen's in a compound with a nonmetal, since nonmetals tend to be negative, or if it's bonded with a metal, and this is when we call it hydride. So we've got H+ is hydrogen ion, but H-1 is hydride. So if you see hydrogen with a metal, that is its -1 oxidation state. And then oxygen, we'll go over several examples. A is by far the most common. If you see, as you can see with barium oxide, barium is +2, is a group 2 metal. Oxygen is -2. And also to note here, if oxygen is in a polyatomic ion, like sulfate or nitrate or any phosphate, carbonate, hydroxide, it will also be -2. So we'll expect to see oxygen as a -2 oxidation state many times. There are a few cases where it will not, and you will probably see at some point hydrogen peroxide, H2O2. And this is a case where oxygen exists as a 2- ion, but it's actually 2 atoms bonded together. So if you take that and split it apart, each individual oxygen and peroxide would be -1. And if you think about it, each hydrogen's +1, each oxygen there would have to be -1. So again, if you see a peroxide like that, that's a special case. And then C, you'll see this very occasionally, but if we keep up with that fluoride rule where fluoride has to be -1, oxygen in that case is going to achieve a kind of an odd oxidation number of +2. But fluoride does get to be -1, so oxygen would be +2 in that case. And as you might have seen from some of these examples, if we just have a compound, oxidation numbers must equal 0. So you can look up above at BaO. That's overall a neutral compound. It has no overall charge. So +2 and -2 do equal 0. And with water, same thing. You've got oxygen is -2, each hydrogen is +1, and overall that equals 0. Number 7 is where we finally get to that permanganate ion example, and we'll look at that on the next slide. But what I'm talking about here is if you just have a polyatomic ion, the manganese will have an oxidation number. Each of those 4 oxygens has its oxidation number, but when we add it all together, we have to achieve whatever that overall charge is. Okay, so these compounds overall are 0, but a polyatomic ion is going to be an overall charge, whatever its charge is, and this permanganate ion's -1. So let's go through and try to assign oxidation numbers. Actually, let's go back and I'm going to go through this permanganate ion example. as I said here, in a compound, oxygen is negative 2, and again, look for that in these polyatomic ions, that you're going to assign oxygen a negative 2 oxidation number, because typically we'll start with oxygen, and since we know it's going to be a negative 2 oxidation number, we can figure out whatever else is bonded to it. So here, if each oxygen is negative 2 and we have 4, think of it as like a little algebra problem. We've got 4 oxygens, each have a negative 2 oxidation number, so that is a total of negative 8. Overall, we said that the charge of all these oxidation numbers added together has got to be the charge of that ion. So you can see we've got negative 8 for all the oxygens. We have to achieve negative 1 overall. Manganese would have to be plus 7. So that's a way to determine manganese's oxidation number from knowing oxygens. So let's go through these. So into, let's see, into is an element. We have that as 0. Phosphide we see is it's a single ion, so that's its charge. And then we get to number 3. And 3, 4, 5, and 6, we actually can take the time and work those out. So again, this is a neutral compound, so we know whatever those 2 oxidation numbers, they have to equal 0. So once you just have like an ionic compound like LiCl, these oxidation numbers are really going to be their normal charges. So we know Li is a group 1 metal, it's plus 1. Chloride is a group 17 halogen, which have charges of negative 1. So that would make sense. So we've got plus 1, negative 1 equals 0. Same thing with number 4 as a neutral compound. Again, so we'll just go with their normal oxidation. Their oxidation numbers will be their normal ionic charges. So aluminum will be plus 3, oxide will be negative 2. When we get to sulfate ion and ammonium ion, that's where it gets a little bit more interesting, and we have to do a little math to figure it out. So we know this is overall going to be not 0. We know that sulfate is overall going to be the charge, which I wrote 0 incorrectly. It's got to be negative 2. If we start again like we did on the previous with permanganate ion, we know that oxygen, each oxygen is negative 2. It's in a polyatomic ion. There are 4 of those, so all the oxygens together are negative 8. So if we have negative 8 for oxygen, we can see that sulfur would have to be plus 6 to achieve that. Then moving on to ammonium ion, a little bit different example. This time its overall charge is plus 1. So we can start from the hydrogen, because again, as I said earlier, when hydrogen is bonded to a nonmetal, it is technically acting like a metal. It has a positive 1 charge, or in this case, oxidation number. So we have 4 hydrogens at plus 1 each. So that's an overall plus 4, excuse me. So we can figure out what would nitrogen have to be to achieve plus 1 overall, and as you can see, it would be negative 3. And these are defined on each of these examples is worked out specifically on the next slide. So what's the whole point? Why do we need to assign oxidation numbers? Well, if we see that oxidation numbers are changing in a reaction, then we can know if we do have an oxidation or reduction process. If oxidation numbers in a reaction are not changing, then we know that this is not a redox reaction. So these are questions you might possibly be asked to answer. So to determine if this is a redox reaction, as you see the question at the bottom, we need to assign individual oxidation numbers, and we can see if any of the atoms are changing in value. So if we have NaCl, again, if it's just an ionic compound, we can just assign normal ionic charges, which are also their oxidation numbers. So we have plus 1, minus 1. If we go over to the products, we see chloride is with silver, and silver is +1, -1, so we can see chloride is not changing, it's saying -1. Over here with silver nitrate, we see that silver is +1, so silver has not changed. And if we go to sodium, we see that sodium has not changed. So then we've got this nitrate. See how nitrates stay in the same polyatomic ion, which is really a clue to tell you that it also is not changing any oxidation numbers. But we can go ahead and work it out to the side just so there's more room. We know oxygen on polyatomic ion is -2. Since there are 3, this is -6 overall. So what would nitrogen have to be to achieve that -1 ionic charge? It would be +5. So if nitrate's staying nitrate, then that means the nitrogen's +5 on both sides and the oxygen's staying -2. So is this a redox reaction? No, it's not. See, this is not redox. All the atoms maintain their same oxidation number as reactants and products. So then we can go on to another example. And we have CH4 methane plus, this is a combustion reaction, plus oxygen gas forms carbon dioxide and water. So again, we can go through and assign oxidation numbers. Hydrogen is bonded to a nonmetal, so each hydrogen is going to be +1. There are 4, so overall all the hydrogens together, hydrogen is +1. All the hydrogens together, I'll just do the math underneath. If methane is neutral, what would carbon have to be to cancel out that? So we can see that carbon here is -4. So we'd have -4 plus +4 equals 0. Oxygen gas, that is your 0 oxidation state. And then you get to your products. So far we have -4 for carbon, +1 for hydrogen, and oxygen is 0. Here oxygen it's in a compound, it would be -2. And if each oxygen is -2, that's -4 overall. So this carbon is going to be +4, which is interesting. And then we have over here in water, oxygen, we saw that earlier, is still -2, each hydrogen is +1. So if we notice, hydrogen is +1 and staying +1. Nothing's happened to hydrogen, but notice carbon is -4 and it's going to +4. That's a huge change. Notice it's going up in value. So if we think about what that process means, and oxygen gas is going from 0 down to -2. So we can see there are changes here. We know this has to be redox, and we can define exactly what's happening. So carbon is going from -4 to +4. Remember, if it goes up, that's oxidation. And if the oxygen, and you could look at either oxygen in the products, it doesn't matter which one you're referring to, but oxygen's going from 0 as a reactant as an element to -2, so that shows that it's gaining electrons and is reduced. One item to note here is that when you're asked if something is a redox reaction, look for elements, either as a reactant or a product. Anywhere there's an element, you know it's got a 0 oxidation number. It's got to be something different as a reactant or product. So, and just the presence of an element in a reaction is a clue that it's got to be redox. There can be redox reactions that don't involve elements, but again, it would be a quick way to notice you do have a redox reaction. Balancing redox reactions, some are going to be simpler than others, but the balancing is unique. We've got this transfer of electrons, and there are some extra steps that are required instead of just looking at a reaction and adding coefficients. So we're going to go through a more involved example and then a simpler example, but let's go through the steps first, and then I'll show you how to apply those. So first of all, when we take this whole reaction, we're going to end up splitting it into 2 half reactions. And I used that term earlier. We're going to actually balance each half of the reaction separately, and then at the end we'll put them back together. So again, you can tell this is a much different type of balancing. So once we've split the reaction into 2 halves, we're going to just balance them one at a time. So the first step is always to balance any atoms other than oxygen and hydrogen. Again, we're still using coefficients, but make sure you do balance all atoms other than O and H first. Then, and again, this is where it's pretty unique. If there's any oxygen on one side of the reaction, we're going to balance it on the other side of the reaction by adding water molecules, as many as are needed to make the oxygens equal on both sides. And a lot of times these reactions are specified in acidic conditions, and so too, which means you have H plus present. So we're going to, since we've introduced water, now we've also introduced, hydrogen that's in water. That needs to be balanced. So we're going to balance the hydrogen from water by adding H plus, as many as needed, to the other side of the reaction. And then once we get to that step, if we had to do 3 and 4, sometimes, there's no oxygen and these steps aren't even required, but we need to balance electrons, because that's the whole point of a redox reaction, is that we've got this transfer of electrons and we need to figure out how many electrons are transferred to keep these charges balanced. So we'll look at each side of the reaction, add up any charges that are visible, and then we'll add these negative electrons to the side so that both charges on each side of the reaction are balanced. They have to be the same value. It doesn't matter. They might be 0, they might be a positive or negative number. The value is not important. It's just that the charges on both sides are balanced as well as the atoms. So we'll go then, after we've done one half reaction, we'll go to the other. We'll do those same steps, repeat that process. Then once both halves are balanced, we'll look at them and we'll look particularly at electrons for number 7. Are the electrons lost, which would be products in the oxidation half reaction, or is that the same value as the number of electrons that are gained in the other half reaction, which would be the reduction half reaction? If those values are not equal, like if one half reaction lost 2 electrons, the other one gained 3, that doesn't abide by the law of conservation of matter. Those electrons have to be the same. So if in that case the electrons are not the same, as you see in bold, we'll multiply the entire half reaction by an integer that would make the electrons balanced. So sometimes you might have 2 electrons in one, so if you just double the half reaction with 1 electron, they would be balanced. The other example I mentioned where there were 3 and 2, again, you might have to, as it says in parentheses, you might have to multiply both half reactions by a whole number so that the electrons are equal. So again, we'll look at examples in just a moment. Once the electrons are the same value in both half reactions, we're going to add these half reactions back together to get back to this whole reaction that will now be balanced. And since electrons are lost in one half reaction as a product and gained in one half reaction as a reactant and should be the same value, they will cancel out. As you probably maybe not have realized at this point, but we don't ever see electrons in a balanced reaction. So those electrons will not be present. They should cancel. So, and then you can do a check at the end to make sure that both sides of the reaction have equal numbers of atoms and that the charges on both sides are equal once you add them back together. Here is an example of the dichromate ion plus chloride going to the chromium ion plus chlorine gas. If you notice, when it says split them into half reactions, sometimes people are wondering, how do I do that? How am I going to know? Well, as you can see, dichromate ion contains chromium, and then you've got this chromium ion by itself. So you can just say, that's going to be half. The other half you can see involves chlorine. So we'll just start. This is reduction. If you go through and do your oxidation numbers, that would be a good practice to figure out what the oxidation number is of this individual chromium, so we'll do that first. If we have each oxygen's -2, we know all the oxygens together would be -14. 7 times -2 is -14, and chromium's overall charge is -2. So 2 times what number plus -14 would give us -2. So again, that 2x term total would be plus 12. So that tells us that half of that, each chromium, would be plus 6. So we've got chromium from plus 6 here going to plus 3. And again, there was not a question to ask us what was reduced in this case. We would answer chromium if that was asked, but if we are asked, that's again, we're citing oxidation numbers, that's how we would know. So once we have this half reaction, we need to go through those balancing steps mentioned and get this balanced. The first step is to balance the chromium, since you have 2 in the dichromate ion and only 1 on the product side. So adding a coefficient of that 2 in front of the chromium ion takes care of that balancing. The next step, as you see the oxygen that's in the dichromate ion, we need to balance that by adding water to the product side. So you see why there are 7 water molecules, because that gives us 7 oxygens. Notice above it says an acidic solution, so that tells us we need to add H plus to balance the hydrogens. There are 7 times 2, that's 14, so we need to add 14 H plus ions to the reactant side. So at this point we need to add up the charges on both sides so we can figure out and determine the number of electrons. So if you notice, you've got, and I'm going to kind of just write down here, we've got positive 14 on the reactant side plus a negative 2. So on the reactant side right now we have positive 12. And on the product side we have 2 times 3, so we have positive 6, and then water is neutral at 0. So here we are with our total charges of plus 12 and plus 6. And if you notice in the next step they've added 6 electrons. So hopefully that you can see why that's being done, because once we add these 6 electrons we've reduced the positive 12, so now both sides are positive 6. And that's what we're looking for here, because we do need both sides to be the exact same value. So that half reaction is balanced. Now we're going to move on to the other half, which involves the chlorine. So you've got Cl minus going to Cl2. Again, the first step, balance atoms other than oxygen and hydrogen. So we've added a 2 in front of that chloride ion. So we balance those. Notice there's no oxygen, so if we don't need to balance with water, which means we don't need to worry about the H plus. We can go straight to the electron step. So on this example, you see the 2 chlorides, that's negative 2 overall, and on the chlorine, and don't forget the coefficient, because a lot of time it's easy to just assume chloride's negative 1, but it is negative 2, so there's 2 of those ions. So we've got negative 2, I'll write it up here, negative 2 on the reactant side, and then chlorine gas is 0. So you can see if we add those 2 electrons, now both sides are negative 2. Now, since both halves are balanced, if we go back a step, we see that we have to remember that we have 6 electrons that we needed to balance that chromium half reaction, but only 2 are required to balance this chlorine half reaction. So again, those aren't equal and they have to be. This is a required balancing step. So what's happened is they've multiplied this whole half reaction by 3. So we've got 3 times 2 is 6 chlorides, 3 times 1 is 3 chlorine gas, and 3 times 2 is 6 electrons. So you can see where that's come from. And then this final step here is where they've taken the previous half reaction with the chromiums, and this new balanced version of the chlorines, and they've added those together. So notice the 14H plus came from the previous half reaction. There's our dichromate ion, and then the 6 chloride. So all the reactants get put back together. And then on the product side, we have our 2 chromium ions, 3 chlorines from here, and then that 7 water. The order that you write the reactants, whatever order you want to write is fine. It doesn't matter as long as you're on the correct side of the arrow. And then the products, again, the water could have been written in between the chromium and the chlorines. It really doesn't matter as long as it's there. But it says, this is balanced. You can check, like I've got 14 hydrogens on the reactant side, and I also have 14 hydrogens here. I have 2 chromiums and 2 chromiums, 7 oxygens, 7 oxygens, 6 chlorines, 6 chlorines. So I know all the atoms are balanced, but it's a good idea to check the charges especially. So here I have 14 positives minus 2, so that's plus 12, and then I've got 6 negative. So I've got plus 6 on this side. And notice these two are neutral, and this side's plus 6. So now this should be the correct answer, and we did a good job balancing. Here's one for you to try. It kind of walks you through it, but I want you to try this on your own. So I'm not going to, we'll walk through the answers in a minute, but I would like for you to take the opportunity to balance each step and go through those, because the more you practice the skill, it just becomes really easy. And the rules, they seem long, but once you've done this a few times, you really don't have to think about it quite as much, and it just comes naturally. So here's that iron half reaction, and again, as I said, sometimes this can be pretty simple. So in this iron reaction, we know this is oxidation. If you hadn't thought about it, maybe it'd be a good time to look at it, because it's 2 plus to 3 plus. Remember, we said if it's losing electrons, it actually becomes more positive. So we see the oxidation number increases. And again, the irons are balanced. There's no oxygen, so we don't have to worry about hydrogen either. We just need to do these electrons. So we do need both sides. So we needed 1 electron in the products. And with the permanganate ion example, this required a little bit more work. And so the manganeses are actually balanced. We needed to balance the oxygens by adding the 4 water molecules, which gave us 8 hydrogens on the product side. So we needed to add 8 H plus ions to the reactant side. And then our next step is to do the balancing. You can see I've totaled these underneath. So permanganate ion is -1. We've got positive 8 from all the hydrogens, and the product side was plus 2. So basically we had plus 7 on the reactant side and plus 2, so that's why 5 electrons were added to achieve that equal plus 2 charge on both sides of the reaction. So now both half reactions are balanced. We're ready to look at electrons to see, because here we have 5, and in the previous example we only had 1. So the electrons are not balanced, and we need to make sure they're balanced. So think about what you would do next to achieve that balancing, and then finish the problem. So hopefully you were going to multiply times 5, and then we can add those together. Then you can check to verify that we do have a balanced, complete reaction that is ready to go. Here's another example. I included this one because a lot of the redox reactions that are used in electrochemistry are actually even simpler than the ones we've done so far. Notice there's no polyatomic ions, there's no oxygen, no hydrogen. These examples you'll probably like these the best. These are the easiest and take the least time to balance, but it's still important that you understand all the balancing rules. So you can work on balancing those half reactions. It's really only going to require you to balance using electrons. So once you balance the magnesium half reaction, and think about that is oxidation, make sure you understand why you're going from 0 to plus 2. Increase in oxidation number means electrons have been lost. In this case, it would take 2 electrons to be lost. For reduction, we have aluminum going from 3 plus down to 0, so the number is getting smaller, and that would be a gain of 3 electrons. So if we see a loss of 2 and a gain of 3, like I mentioned earlier in the notes, that is not balanced. So both half reactions would need to be altered or multiplied by an integer so that the electrons will cancel. So if we multiply the aluminum half reaction by 2 and the magnesium half reaction by 3, we have 6 electrons, and we can add those together, and now we have a balanced reaction. So now that we understand how to assign oxidation numbers, you know what oxidation and reduction are, we can actually talk about a battery that we mentioned at the very beginning. So first we're going to study one of the two types of electrochemical cells. These are really applications of how redox reactions are actually used. All batteries are called galvanic cells. Another term you might see is voltaic. I'll write that out. It's an older term. I still see it in textbooks and old AP questions, but it means galvanic. So either one is good. And batteries are made of, different components depending on the type of battery. Like your car battery is considered a wet cell battery, very different from dry cell batteries like AA, AAA, those kind of things. But the commonality between all kinds of batteries, no matter, it's just that even no matter what their components are, they all have in common that they're chemical reactions that produce electrical energy we're using to do some work for us. We will discuss the other type of electrochemical cell later. It's called electrolysis, or they're electrolytic cells. And this is really the opposite of a battery. This is like charging your cell phone. Is you're taking electrochemical cell and adding energy to it. So completely different process, and will be discussed later. So for a galvanic cell, we're going to start off talking about the parts of it because it has some really important, and these might be new terms for you, but they're easy to remember. There's an anode. And this is the part of the cell where the oxidation process is occurring. If in the oxidation half reaction you have a solid metal involved, which in oxidation that solid metal would be a reactant, what's actually going to happen is the mass of that solid would decrease. Okay, so that's not going to happen in every cell, but if there is a solid involved in oxidation, that mass will actually be decreasing. And there's some really great mnemonic devices which do help a lot of students remember which process is occurring where. So anode is where oxidation occurs. So ox, it's kind of helpful. And then the other part of the galvanic cell is where the reduction process is occurring, and that is called the cathode. And when we have reduction, if there's a solid metal involved, that solid metal, since we need the oxidation numbers to go down, you would actually have, like if it's a metal ion, like we saw copper 2+, would gain 2 electrons to go to solid copper. If there is a solid metal involved, you actually would see the mass of that electrode go up because you're producing more solid as part of that reaction. So we call this the red cat because reduction occurs at the cathode. We do have an instrument that measures what we call cell potential of the battery. This is when you hear the word voltage, like a 9-volt battery. That tells us, and the voltmeter is measuring that energy that's traveling through the cell, and that's the energy we're using to do work. A wire would connect the anode to the cathode. The wire goes from the anode to the voltmeter and then to the cathode. And the electrons, and this is pretty important, you might want to put a big star by this, the electrons leave the anode, because think about it, the anode's oxidation, that's where electrons are lost in that half reaction. And the electrons are going to be traveling through the wire to the cathode where they want to be gained to cause reduction. And so the mnemonic device here is kind of a stretch, but flow of electrons is from the anode to the cathode. Now in a galvanic cell, and we'll see a picture of this in just a minute, but there's a pretty important component. Well, in fact, the battery cannot operate without this, but it's called the salt bridge. This is a connection, and it's a different connection beside the wire. They're two separate things. This connection between the anode and cathode is going to contain usually a dissolved salt, and it typically is a salt that is made up of spectator ions, meaning ions that aren't going to react with anything. We just want these ions to be present, and their purpose is, as this says, to maintain electrical neutrality. And really what that means is as electrons are leaving the anode and traveling to the cathode, you have this oxidation occurring in one half cell and the reduction occurring in the other. The ions that were previously dissolved in the solution become in different, the ratio of those ions changes, and we'll get into this detail in just a minute, but we need these soluble salts in the salt bridge to provide cations to neutralize the buildup of negative ions, and we need anions from the salt bridge to go to the other cell to neutralize or even out the buildup of positive ions. So the bottom line is cations from the salt bridge flow to the cathode, and anions from the salt bridge flow to the anode. The salt bridge, and examples I've used in the lab would be like a piece of filter paper that's been soaked in like sodium nitrate or potassium nitrate. There was a free response question where the salt bridge was actually a paste, electrolyte paste, and there are other labs you might do. I don't. Science of Motion has one where it's actually a porous cup, so that the ions from both solutions can kind of go through the cup. But all of those are acting as a salt bridge. So KNO3 is a very good component. Again, we don't want ions that are going to cause other reactions. We just want those ions to be present in the solution, not to react with anything. Embedded is a galvanic cell. It's an animation, and it does a good job of discussing this new vocabulary of anode and cathode, and it actually shows that the process is occurring at each electrode. I think it's really good. So look for what's being oxidized and reduced. Here is a similar depiction of what would be seen in the video. And the one thing I wanted to point out, because I think because we're used to seeing reactions where you add two things together and it produces products, this is a little unusual because all components, reactants and products of the reaction, are present before the reaction even begins. So I'm going to zoom in a little bit. Notice in this excuse me in this cell on the left, in the solution we have zinc ions and nitrate ions, and then this piece of metal, and this is what I'm calling the electrode, that's dipping into the solution is made of zinc. Okay, so when we see a piece of metal dipping into a solution that contains its ion, those, you can tell the metal and that ion are going to be in its half reaction. And this is telling us underneath that beaker that zinc is being oxidized. Okay, and we'll see why in a minute. Also notice on the surface, the reason the anode is labeled as that piece of metal, that piece of zinc metal, that electrode, is because it's where the zinc is touching the zinc ion solution. On the surface of that is where that reaction is taking place. So notice what's happening is this solid zinc, you see the arrow, is going into the solution as a 2+ ion, and the electron is traveling, and as you can see above, it's the electron that's traveling. Electrons are traveling through the wire. That's your voltmeter with the value that's given in volts, and that's going to be traveling to the other side, to the cathode. Before we talk about the salt bridge, let's go ahead and look at this other side of the diagram, and it's telling us that Cu2+ is going to gain these 2 electrons to become copper solid. So again, where we have reduction is the cathode. These electrons show up here. What happens is, and you can see this in the diagram on the surface, that the 2 electrons on the surface of the copper come in contact with the 2+ ion. The ion gains the electrons and causes that ion to change to a solid atom, and notice it's plating on top of the existing copper that's already there. So when we talked about mass being increasing or decreasing, if there's a metal involved, if we go over to this side photo, you can see that as the reaction would take place, the zinc anode, because the solid zinc is changing to a zinc 2 plus ion after it loses the 2 electrons, the electrode actually gets smaller. Its mass decreases because the mass that's missing has gone into the solution as a 2 plus ion. And notice the opposite's happening on the copper cathode. The copper ions from the solution are gaining 2 electrons and plating on top of that already existing copper. So that mass is increasing. So that was what was meant when I made those statements, just so you understand that a little bit better. Okay, back to our picture. We see this salt bridge is made of sodium chloride, and what's happening here, and I'll try to just give you a little bit more detail about this salt bridge, is, as I said, the anions, negative ions from the salt bridge will travel to the anode. Well, you know, again, it's to maintain electrical neutrality, but it's why. Why does it need to do that? Well, if you think about what's happening in the solution, before this redox reaction is taking place, in this solution you have dissolved, you see the salt that's dissolved, zinc nitrate. So for every 1 zinc 2 plus ion, there are 2 nitrate ions. That's what's dissolved in the solution. Once this reaction starts occurring, the zinc, the solid zinc is losing 2 electrons, and more zinc 2 plus is entering the solution. So what's happening is we had this balance of zinc 2 plus and nitrate ions, and once more zinc 2 plus is going into the solution, the amount of nitrate ion is not changing, so we basically have this buildup of positive, extra positive charges. This extra zinc 2 plus is going into the solution. That's why anions, some kind of negative ion, is needed to neutralize that, because the electrons cannot leave. Think about it. Electrons are negative. If this is a buildup of positive, a negative would not be able to leave a positive buildup. So we need these extra negatives to flow from the salt bridge and be attracted to the zinc 2 plus ions. They're not going to form precipitate or anything. They're just going to enter that solution. That allows the electrons to leave. So what's happening in the cathode compartment? Well, what's happening is that when the electrons come in, the copper 2 plus is attracted to those electrons, and as we said, is plating on top of the already existing copper as new solid. So what's happening, if you go take a step back, in this solution we've got this copper 2 nitrate solution. For every 1 copper 2 plus ion, there were 2 nitrate ions dissolved. So if copper 2 plus ion is leaving the solution, okay, what happens here is we're some of the positive charges are becoming a solid, so there's a buildup of negative ions. So we need the cations, in this case sodium ion, to flow into the beaker from the salt bridge to maintain that neutrality. So that counteracts that buildup of charge. So that's the basics of what's going on with that salt bridge, and we're going to address what's going on with the voltmeter in just a minute. As you can see, this example is also giving you the balanced reaction at the bottom. And notice that the zinc half reaction lost 2 electrons, the copper half reaction gained them, so it was easy to balance. It was just a matter of putting those two together because their electron transfer was already equal. And I'll just kind of go through these as a reminder. If you have a metal dipping into a solution that contains its own ion, then those are going to be the components of its half reaction. Okay, there are cases that we will see where there are 2 ions in the half reaction, like we've already seen earlier. We had an Fe2 plus, I believe, and an Fe3 plus ion, or we'll see it later if not. See, neither of those are solid metal. So if both components in the half reaction are ions, they were both dissolved in the solution, and we would need an unreactive substance to we'd need the electrode to be made of an unreactive substance. So platinum is a choice, which is pretty expensive. In most cases, we would use something like graphite, literally you could take a piece of your, what we call pencil lead. It's really graphite, but you could take out of your mechanical pencil a piece of that lead and use that as an electrode. And that would be just a way for the electrons to get out of the solution. So again, I've kind of gone through all these examples. One thing to note is, nitrate ion that was part of that dissolved salt in the solution in both half cells is not part of the reaction. Notice that these are net ionic reactions. Nitrate ion is a very common spectator ion. It's not going to be involved in any reactions, and that's why it is not included in either half reaction, nor is it included in the overall reaction. Okay. When we get to questions to answer about galvanic cells, they've given us all the information. They've told us anode, they've told us cathode, they've given us the balanced reaction, the cell voltage, they've shown us how electrons are flowing. These are questions you're going to be able to answer from the information given. And again, I've included some questions that you really need to think about. How could I answer this? So how can we determine and label which half reactions could be oxidation or reduction? And this is really where this voltage comes in. With each question, you'll be given a table of reduction potentials. Okay, and we say potentials, think of voltage. Okay. And we'll talk about this a little bit later too. These values, these voltages, indicate how likely a substance is to be reduced. So we're going to for each half reaction, we're going to have a voltage associated with it, and from those values, we'll be able to tell what's oxidized and reduced. And here's the key: the more positive reduction potential indicates the substance that will be reduced, and therefore whatever the other value is that's lower, that substance is the one that's going to be oxidized. So let's look at an example. So here we have the two half reactions that we just kind of looked at. Notice that they're both listed as reduction, and notice that's the title, standard reduction potentials. These are always typically given as reductions, and from this information we can know what's actually going to be reduced and what half reaction would be reversed and become oxidation. Okay, so if you think about it, if you take any half reaction and you flip it, now you have, instead of having electrons on the reactant side, which indicates reduction, if we reversed it, we would have electrons on the product side. So as we said before, the more positive reduction potential for a galvanic cell will remain reduction. So notice for these two values we have positive 0.34 and negative 0.76. We can see that copper has a higher value. It will be the reduction. So this one will stay just like it is. Okay, nothing's going to change. That one's going to stay reduction. Now, the other half, again, we can't have two reductions. If something's gaining electrons, they have to come from somewhere, so we have to have oxidation. That tells us this lower value that we see here, that is going to be have to be changed to be oxidation. So since it's a lower reduction potential, we're going to reverse the reaction like I mentioned. Okay, that's oxidation now. And the other key is, and you can't forget to do this, is because we've reversed this reaction, its potential changes sign. Okay, so now this is a reduction potential for copper, and now since we've reversed the zinc, this is what's going to be oxidized, and now we call that an oxidation potential. So how did we get 1.10 volts on the voltmeter? It's just a simple addition problem. We're going to get this standard, it's called standard cell potential, or I called it the overall voltage, same thing. We're going to take the reduction potential, which we see is that 0.34 volts that's listed in the table. Notice we're adding it to the positive 0.76, which is the oxidation potential once we reverse the zinc. That's how we got the 1.10 volts. And this is something you're going to be asked to calculate. And another question is, how do we get the balanced reaction? I mentioned this earlier. This balancing, is very simple. It's just a matter of putting them back together and canceling out your electrons because the electrons were already balanced. Now, I'm not going to read through this again, but these slides explain exactly what I was saying about the salt bridge. It'd be good to read over that again and make sure you're understanding. The whole purpose of the salt bridge is to neutralize charges that are building up. So cations, and you need to mention the specific cation. So cations in this case, sodium ions will flow to the copper cathode, and chloride, the anions, will flow to the zinc anode. So again, it's a good general statement, cations to the cathode, anions to the anode. But if you're asked to explain that, especially like in a free response, you need to mention the specific anion that's flowing to what you're saying is the anode. In this case, it was zinc, and the specific identity of the cation and the identity of the cathode, in this case, copper. So, what if there's no salt bridge? This is a pretty common question that happens. If there's no salt bridge, the charges build up, the electrons cannot flow. So the voltmeter would have no reading. It would have a reading of 0. It would not be producing electricity. And again, this is just talking about that change in mass. Metals that are oxidized actually lose mass, and metals that are being reduced, that you're plating new solid on top of the existing solid. And this question is pretty important, and this was on a AP exam not too long ago. It says, where does the mass go? And there's some really interesting answers that came up with, but the key is ion. See, even though zinc has gone from solid to zinc 2+, it's only lost 2 electrons. When we do like the mass of an atom, we don't even consider the mass of electrons. Electrons do have mass, but it's just so small compared to the mass of protons and neutrons. So the mass of an atom comes from protons and neutrons. So if only 2 electrons are lost, the mass of the atom is remaining with the ion. So again, the ions are maintaining that mass. So the solid zinc loses 2 electrons. So the mass of the solid zinc electrode is really going into the solution as that ion. Now when we talk about, I've mentioned cell potential and voltage, here's really the definition of what that means. Cell potential or voltage is the measure of electromotive force. It's really the pull of electrons as they travel from the anode or cathode. It's that attraction that's pulling them. Common symbols are E cell, EMF you might have seen in other contexts. We're going to be looking at E cell or E naught cell, and we'll talk about that naught symbol in just a minute. But the unit is a volt, and it is that capital V. I've had students ask me, where are they getting these numbers from? So if you wondered that or not, it's pretty simple. It's just they took hydrogen gas as the standard, and they assigned its half reaction as a voltage of 0, and then they put every half reaction on the other, like as a galvanic cell, and they compared it to hydrogen gas. So if whatever was compared to hydrogen gas was reduced, it would have been a more positive reduction potential than hydrogen, and if something was paired with hydrogen gas where hydrogen gas was caused to be reduced, then that other substance was given a negative value. So the standard is hydrogen gas, and again, it's just everything, these values are coming from that comparison. Now, standard conditions, that is, every time you see this, it looks like a degree symbol, like degrees Celsius, but it's really pronounced not, and it means standard conditions. So when you look at standard reduction potential charts, they will tell you this was 1 molar solutions at 25 degrees Celsius, and that's why those piece of information will be given, because that knot symbol does indicate that specific lab temperature, that molarity for solutions. And if we had gases, they would be at a pressure of 1 atmosphere. So here's a good example for you to try. In this example, this will give you a good opportunity to try and see how you're doing on understanding this information. So again, number 1, determine the anode and cathode. Calculate the standard cell potential. Describe how the electrons will flow through the wire. Write the balanced net ionic equation. And number 5, describe how the K+ ions will move from the salt bridge. So you might pause and give yourself time to really answer all these questions specifically. So for number 1, we have these 2 reduction potentials given in the table. As we said earlier, the higher potential will stay reduction and the lower one will be reduced to be oxidation. So nickel would stay reduced and its value would stay that negative 0.25. The zinc half reaction would be reversed, and zinc would become oxidation, and we'll see that its cell potential will also be reversed as well. So the question is, what's the anode and cathode? The anode is zinc, since it had the lower reduction potential, so it is reversed, and nickel is a cathode, and it's reduced with the higher potential, and reduction occurs at the cathode. Number 2, this calculation, again, the nickel stays negative 0.25. We've reversed zinc to be oxidation. Just the addition of those two gives us this positive 0.51 volts. Number 3, how do the electrons flow in the wire? We know that they flow from the anode to the cathode, but we need to specifically mention that the electrons would leave the zinc, that because it is the anode, travel through the wire to the nickel cathode. A lot of free responses, they might actually ask you to draw this on the wire, like on the diagram. So you could just do arrowheads to show which direction they're going. For the balanced net ionic equation, and again it says net ionic because if you notice, both solutions contain the nitrate ion, but as we said earlier, nitrate ion is a spectator. It's not involved in the reactions, and that's why it is not included in the half reactions nor in the overall balanced equation. Again, we're fortunate that the electrons are already, the number lost is equal to the number gained, so there's really no other adjustments except for just adding these together and not including the electrons. And 5, it's only asking about the K+ ion, so remember that's a cation, and just think cations, cathode. So the K+ ions would be moving from the salt bridge towards the cathode, in this case the nickel. So they're trying to neutralize the buildup of charge as the nickel 2+ ion is leaving the solution as solid nickel. I want to take a minute and talk about non-standard conditions. We did talk about that not sign, which designates standard conditions. Well, what if we don't have standard conditions? And for electrochemistry, that's only going to be a situation where we have solutions other than 1 molar. The key to this is looking, because you'll have 2 ions typically. One is a reactant, one is a product. Could be more, but at least 2 ions. You need to know which ion is a reactant, which ion is a product, because we're going to make a ratio of these molarities. So the product, whichever ion is a product, and again brackets mean molarity, so whichever ion is a product, its molarity would go as the numerator in this ratio, and whichever ion is a reactant is going to go as the denominator in this ratio. What you're really looking for here is this ratio greater than 1 or less than 1? Okay, so if the ratio is greater than 1, okay, and this ratio is really called Q. I'm going to go ahead and tell you this here. Q is the reaction quotient. This really comes from a formula that is not required to be solved mathematically anymore, but you still are expected to understand the relationship. So again, back to, is the ratio greater than 1? If the ratio is greater than 1, what this is saying is that there are more products in the solution than reactants, so that overall the non-standard cell potential will be lower than the standard cell potential. So those extra products are preventing the reaction from going in the forward direction like it normally would have. So the measured voltage would be less. Number 4 just says, well, what if the ratio is less than 1? So what if we had 1 over 2? So that would be 0.5. If the ratio is less than 1, notice the reactants are in the denominator. So if the ratio is less than 1, the non-standard cell potential would actually be higher than the standard value. We have more reactants present than products, which allows the forward reaction to be greater and to produce more voltage. Now, where does this really come from? And it really comes from a formula called the Nernst equation. It's not on the AP exam anymore, but if you kind of just look at this generally, it helps you understand why this ratio is such a big deal. And really the math explains it, everything on the other slide, a little bit better. Now this Nernst equation is valid for 25 degrees Celsius. There's also another version of the Nernst equation which has a few more variables, but at 25 degrees Celsius this version holds true, and this was the version on the previous formula sheet before they changed the exam. Notice here's our standard cell potential that we've been solving for. We're going to get to N. We'll see this in a minute. N, we always think of like in PV equals nRT, N is moles. For electrochemistry, it's still moles. It's just we're talking about moles of electrons. This is that balanced number of electrons. Okay. This 0.0592, this came from the temperature and some other constants. So that's just a derived value from some constants. And then here's that Q I was talking about. It says Q is the ratio of products to reactants. And really, technically to be correct, these are raised to exponents, and the exponents come from coefficients in the balanced chemical equation. And this is in the notes. Again, I do get my students to solve this a few times, and some of them try to remember the equation just because sometimes it's easier to explain if you're asked about molarities being changed. Instead of talking about it generically, they can just solve it and have, this non-standard E. It's just sometimes easier to talk about, is it greater than or less than the standard cell potential. But, that's kind of a personal preference. So what I was saying was, if Q is greater than 1, if you take the log, that's the logarithm button on your calculator, the log of a number greater than 1, it is a positive number. So then when you multiply times 0.0592, divide by the number of moles, that's a subtraction. So if you've gotten the log of Q as a positive number, even no matter what math you're doing, you're going to be subtracting from you're going to be subtracting this whole term from the standard cell potential. So, as I said on the previous slide, if the ratio is greater than 1, the non-standard potential is going to go down because it's going to be subtracted here. Okay? So if we plugged in a 2, you could do the math, and you would see that, whatever the standard cell potential was, you would be subtracting. Okay? Now, if we could talk about the other scenario, and I guess it's in the notes. If I plugged in a fraction, like if the ratio was 1 over 2, I'm really plugging in the log of 0.5. If I plug in a value that's less than 1 and take the log of it, and you can try this in your calculator, just plug in, hit log 0.5, and you'll see it's negative, or any number less than 1. What happens is, no matter what math we're doing in that term in parentheses, if you're subtracting a negative answer, you're adding. So that's why I'm saying that the non-standard cell potential will actually be higher when you have Q that's less than 1. So that's where that whole slide came from, just to get a little background information. And it's also in the notes. Okay, so we're back to talking about voltage and energy. There's a relationship you need to be aware of, and we've talked about what a volt is, but really kind of the details of it. So we have this electromotive force, which is what we call voltage, is equal to really work over charge. Okay, work measured in joules, and charge is measured in coulombs. So that might be a new unit. Notice these have been rearranged. The units have. So joule is equal to volt times coulomb, and then those are the abbreviations. And I'll just read this next statement. The work that can be accomplished when electrons are transferred through a wire depends on the potential difference, that's that EMF, in volts between 2 points in the circuit. And then 1 joule of work is produced when 1 coulomb of charge is transferred between 2 points in the circuit that differ by a potential of 1 volt. And a coulomb is just that quantity of electrons, which is charges that are passing through the circuit. So just kind of background information. You just need to understand this unit relationship. Okay, so that just gives you a little bit of extra background so you understand those units, because we're about to apply that. Now, we have this concept called Gibbs free energy, and it will be discussed a lot in thermodynamics. So just for right now, just realize all we really need to understand about Gibbs free energy is the sign of it tells us if a reaction is going to happen or not on its own. Okay, so, and when we say a reaction happens on its own, it doesn't have to be fast. It might be a very slow reaction, but if a reaction is going to occur without outside intervention, that means it's thermodynamically favorable. The conditions are right for that for those reactants to form products. Okay, so here's what you need to connect. Thermodynamic favorability means that this term, delta Gibbs free energy, must be negative. Okay, so that just means a reaction is going to happen. Now, batteries, if they're connected properly in your calculator or, cell phone, whatever, those are chemical reactions that occur on their own. So we say galvanic cells, which are batteries, are thermodynamically favorable. Okay, so again, this is hugely important. It'll be covered in lots of different contexts throughout the year. Now, there are 2 formulas that deal with delta G that are related to electrochemistry. So we're going to go ahead and look at those, and you'll see why I had the slide about the joules and volts and coulombs in a minute. So here's the first one, and here are all the variables defined. So G is Gibbs free energy. N, we saw it's part of the Nernst equation. You are expected to know that, and all these are defined on the formula sheet as well. N is that number of moles of electrons that are transferred. This is the balanced number from the half reactions that cancels out. Because if we have 1 half reaction losing 2 electrons and 1 gaining 3, what would you plug in for N? You can't plug in 2 or 3. You would plug in the balance value, which would be 6. F is a constant. It's called Faraday's constant. It's actually the charge in coulombs of 1 mole of electrons. So it's 96,485 coulombs per mole of electrons. So if we have 6 electrons transferred, 6 moles transferred, it would be multiplied, as you see, N times F. And then the last term we've seen already is that standard cell potential we've been calculating by adding the reduction potential to the oxidation potential. So if we go back to our nickel and zinc galvanic cell example that you worked on your own, our cell potential was 0.51 volts. So if you're asked what's the value of delta G, I just wanted to show you how you would plug in values and get the correct answer. So in both of those half reactions, we had a loss of 2 electrons and a gain of 2, so N is 2. Faraday's constant is from the formula sheet, and then we would plug in the cell potential we had added together to achieve. So you can see we've multiplied those 3 terms together. Moles of electrons cancel out, and we're left with volt times coulombs. And what is that equal to? That's a joule, which makes sense. That's an energy unit. And typically delta G is measured in kilojoules. In this case, unless it was specified, you'd be welcome to leave it in joules, or you could divide by 1,000 and get it into kilojoules. Both are correct. And another question that's very typical is this reaction thermodynamically favorable? If you're ever asked that question, you need to just know the sign of delta G. So in this case, we'd say yes, delta G is negative, therefore it's thermodynamically favorable. And then the other formula involves a quantity called K, which is the equilibrium constant. We know that galvanic cells, which are what we call batteries, are reactions that are occurring on their own. We know that reaction, those reactants are reacting together to form products. They're going forward. We call that a forward reaction. Another way to say that is that products are favored. And you'll see this. My pen's not working. Anyway, so I was going to write products are favored, but it's not working out right now. So just remember that if the forward reaction is favored or products are favored, we can speak of that in terms of this K. All right, and again, equilibrium is a huge topic in AP Chem as well. It's its own big idea, and that will be covered in great detail, but we can talk about it generally here as well. K actually has no units, which I know is super unusual because you're used to having to worry about those, but K really describes how the reaction proceeds and is this ratio of products over reactants. Now I know we've seen this before and we called it Q, okay? And again, the products and the reactants both are raised to the coefficient in the balanced chemical equation. Okay, so both of these could be raised to a value based on coefficients. Now, what we're looking at here is basically what is the value of K. Just like when we said Q and K, and we'll get into this discussion in later units, but you know, Q was that ratio, K is the same ratio. The main difference is K, these molarities we know are at equilibrium. Q, it's unknown as to where the reaction is. So again, I know that's a lot of detail right now, but what you really need to worry about here is K greater than 1 or less than 1? If we know a reaction is happening, that means the reactants are reacting and forming products. We know that's going forward. So this bulleted point here shows you if a reaction like a galvanic cell is going forward, it is producing a lot of products from the reactant. So that ratio is going to be greater than 1 because that means you have a lot of products over a diminishing amount of reactants. So the value of K can also predict the sign of delta G. So just like we saw in the first delta G formula, if we have a positive cell potential based on the formula, I'm going to go back to that. If we have a positive cell potential, then we would have to have a negative delta G, because if you're plugging in a positive value here, delta G would have to be negative. And the same thing with K. If K is greater than 1, then delta G will also be negative. And we'll look at that formula right now. So here's the second formula. Delta G equals negative RT, and those are multiplied together, times the natural log of K. And let's go ahead and define these terms, and we'll talk about what natural log is. G is, again, Gibbs free energy. And we're, again, the sign of delta G will tell us about thermodynamic favorability. R, you've seen this before with PV equals nRT. It's the same R, except it's a different value than what we've used in gas laws. Okay, so be careful with this. There are several versions of R on the formula sheet, and since we're talking about energy, there is one gas constant that involves joules, and so 8.314 joules per Kelvin mole. So again, you just want to be aware of that, because you don't want to. It is a common mistake, unfortunately, that students will plug in the wrong value, and that just obviously is going to cause a lot of problems. T is temperature, just like so. This RT is the same RT from PV equals nRT with the different R value. ln is natural logarithm. This is a button on your calculator. It is, in my calculator, it's right below the logarithm button. It says ln, and it's just as a log is a base 10. Ln is not a base 10. It's a different. It's just based on a different. Slightly different. So, and then K is the equilibrium constant, which again, as we said, has no units. So if we know that K is greater than 1 and we do this math, delta G would have to be negative. If K is less than 1, and you could try this, you could plug in a number and try it, then delta G would be positive, which does tell us that this is thermodynamically unfavorable. But since we're studying galvanic cells right now, we know delta G is going to be negative because they are favorable. So again, if we go back to that example from before, here is the unrounded value we had for delta G. The temperature would have to be given, and it would be standard lab temperature of 25 degrees Celsius. And you would be asked to calculate the value of the equilibrium constant. We don't want to use unrounded numbers. It just introduces a lot of error. So notice I have the unrounded number. Here's my R value. My Celsius, 25 degrees Celsius, must be in Kelvin. And then we got the natural log of K. So I wanted to kind of specifically go through this math because you may not have used that. You may not be in a math yet where you have to use the natural log. So, I've divided RT to the other side. So once I do that math, I get the value of 39.72 equals ln K. If you look at your calculator, you'll notice right above the ln button is e to the x. What we're doing is we're taking this value out of this natural log. So the way you would type this into your calculator is you would hit second ln, and then that e with the flashing x would pop up. You would insert your 39.72, hit equals. Now we have the value of K, 1.78 times 10 to the 17th. K is much greater than 1. There's no doubt this reaction is going forward. But just as a wrap up, if we're going to have a battery or a galvanic cell, our cell potential has to be positive, delta G must be negative, and K is going to be greater than 1. Okay, now we're going to move on to the second type of electrochemical cell involved in electrochemistry, and it's an electrolytic cell, or you might see the process of electrolysis referred to. The best way to really start this is really to start from what we've already studied, and so we've been talking about galvanic cells for a while, and so let's just look at these two pictures and really see what's the main differences that you see right off the bat. And this is a good way to, really we're going to be comparing and contrasting the two to see how they're alike and how they're different, because they do have some similarities as well. I think most students notice, first off, that, here with the galvanic cell, we have this light bulb, and then over here with the electrolytic cell, you have some kind of power source. There's some energy being plugged in. So I think that's obvious. A lot of times, this is supposed to designate a salt bridge, and as you notice, there's no salt bridge in the electrolytic cell. Some commonalities we'll get to is that they both have an anode and cathode. Electrons are still flowing. And then another difference you might notice, this is supposedly two containers, and this is one. So again, all this will be discussed as we go through the next few slides. Okay, so again, we've said most of this already. A galvanic cell we've talked about is, we're measuring the voltage it's producing, and then this is requiring power for it to work. We've got two containers versus one, salt bridge, no salt bridge. And if you didn't notice these signs, this is not something that's really important that you need to focus on, but I think if you've looked at like any battery, you notice it has a positive and negative pole. So a battery has a positive cathode, that's the cathode, and then the anode is negative, and it's just the opposite on our electrolytic cell. Other differences, and this is what is really what we're going to focus on. These are pretty important. These aren't as obvious you can't see these from the drawing. But if you go back to galvanic cells, and so far, every time we've looked at one, we've taken the highest or the most positive reduction potential, and that's reduction, and the lower value is that half reaction that we reversed to be oxidation. And due to that process, those first two things stated, because of these two, we had a positive cell potential. And because the cell potential is positive, based on that delta G formula, it's negative, and we just went over that K is greater than 1. So, because of, this process, it kind of led into all this other information. Now, this is where it gets, it's very different, okay? And you really have to focus on what kind of cell do I have. Mostly you're going to be looking at galvanic cells. Occasionally you'll see electrolytic cell. These are opposites. So if you think about them being opposites, that might be helpful. So for electrolytic cell, notice it says the most positive reduction potential and half reaction are the ones reversed. So again, hugely different. It's the complete opposite of what we're doing with a galvanic cell. So the lower reduction potential stays reduction. So when you take those two together and add them, you will always get this negative cell potential. And because that cell potential is negative and you plug it in that delta G formula, you're going to get a positive value. And then K is going to be less than 1 because this is a reaction that favors reactants. It's that energy you're adding, you're forcing it to really a non-favorable reaction to happen. Okay, they do have a few things in common. Oxidation is still at the anode, reduction is still at the cathode, and electrons are still flowing from the anode to the cathode. So everything's not opposite. So I just wanted to point that out because sometimes students assume that everything is kind of backwards, but the anode is always where oxidation occurs and the cathode is always where reduction occurs. And again, this is just kind of a summary of what was in the other table about these signs of these quantities that you'll see and be asked about. And so let's look at an example because, it's great to look at all the information, but you have to be able to apply it for yourself. So here are two different half reactions. You can tell they're half reactions because we see electrons. You can tell they're both reduction because those are electrons as reactants. So if you were asked to write a balanced net ion equation for the electrolysis reaction that would occur in the cell, so that tells us what we need to adjust. So again, think about how you're going to use those values. If it's electrolysis, then you're going to calculate the cell potential and answer, is this going to be thermodynamically favorable or not? So take some time and work through those 3 questions. So if this is electrolysis, the lower reduction potential will stay reduction. So that means we're going to leave this just like it is. And we're going to take this higher potential and reverse it and its sign. And it's like I've actually done 1 and 2 out of order, but again, you'll have that same information. So this is staying reduction. We've reversed this to be negative. Once we add those two together, we do get the expected negative cell potential of and it is negative 8.89 volts. So for the balancing for this, again, the oxidation, this is the half reaction that's going to get reversed since it's higher, and this is electrolysis. It has a transfer of 4 electrons, so that causes us to double the copper. And so when we add those together, we end up with 2 water molecules and 2 copper 2+ ions yields oxygen plus 4 H+ and 2 copper solid atoms. And then the third question, was this thermodynamically favorable? And the answer is no. Since the cell potential is negative, that would also cause that would cause delta G to be positive. That will be corrected. So this is a positive delta G, and that's why it's thermodynamically unfavorable. And the last topic we'll talk about is electrical current. And voltage and current aren't the same thing, and so we need to define current. Current is really a rate. It's how many coulombs of charge, which are electrons, pass a given point per second. Its symbol is a capital I. This formula is on the formula sheet. I equals Q over T, so current equals quantity of charge per time. Then you've probably heard about current because you've heard of amps, AMP, and then amps are really, if you remember what Q, we talked about coulombs earlier with Faraday's constant, but amps are coulombs per second, and so you'll see this a lot. So just remember, this is pretty important. Amps are coulombs per second. That is also on the formula sheet, so that will be helpful. Okay, so here are the questions that you could possibly be asked some portion of these. So how long must a current be applied to a solution to plate out a metal, or what mass of a metal will plate out if a current is applied to a certain amount for a certain amount of time? So we can do dimensional analysis to answer these. So how long must a current of 2 amps be applied to a solution of silver ions to plate out 11.5 grams of silver metal? Now this is a time question. So again, if we think about our that we're given amps, that is where our time unit is going to come in. So that's really a calculation we'll have to do at the end to answer that question. What we really need to know is based on how much silver is expected to be plated out and the electrons involved, how much charge is going to be involved. So we really need to focus on finding these coulombs. Okay, so if we start with mass, every time we have mass, pretty much always we change it to moles. Okay, since this is a silver +1 ion, there's only 1 mole of electron that's going to be involved in this half reaction. So for every 1 mole of the solid, there's 1 mole of electrons. And then this is where you have to remember to use Faraday's constant. This is the connection between the half reaction and the quantity of charge. So by multiplying times Faraday's constant, now we have coulombs, and then we can plug into the formula. You could have gone on with dimensional analysis. I'll just show you that. Instead of doing this other set, you could have actually plugged in 2.5. We said it's 2.5 amps, which is also 2.5 coulombs per second. So if I invert that, so coulombs cancels out. I would divide, and then I would also have seconds the same way. So again, you can use the formula or just continue with dimensional analysis. It works both ways. There was not a time unit specified. I just changed it to minutes because that's kind of an unusual number of seconds. But again, if no time unit is specified, it would be fine to leave it in that unit. Number 2, the other version of this is really the same question going in reverse. What mass of copper metal will plate out if a current of 4.5 amps is applied to a solution of copper to nitrate for 35 minutes? In this question, we know time and current, so that is a way for us to know our coulombs, our quantity of charge, and from that we can work towards, with Faraday's constant, electrons, and then change moles to grams. So notice I used the formula here. I plugged in my amps, and I changed my time from minutes to seconds. And so I multiplied to get 9,450 coulombs. And here's my Faraday's constant again. If we have coulombs, we can make a connection to our half reaction and the electrons. So dividing by 96,485 coulombs, that gives me 1 mole of electrons. In this half reaction, since it was copper 2+, we know 2 electrons are involved whereas we only had 1 with the silver ion because it was +1. So we're dividing by 2. Once we have moles of copper, we can use the molar mass and get the mass of copper. And that's the end of electrolysis. So again, the major topics that we've reviewed are assigning oxidation numbers, identifying redox reactions and being able to balance them, being able to identify parts of the galvanic cell and determining information from a galvanic cell, and then contrasting that with electrolysis, and then this last example and calculation with current.